I think now you can see my monitor. Now we are here. This is the last lecture in this week, which is the linear momentum and collisions and the rocket example. We discussed this week the work and energy, the potential energy, and the momentum. And we have the second midterm and the review. The review will be ready today, and the exam will be open for tomorrow. Any question about this? I think I have now 12 or 13 questions for the exam. I don't know, maybe I will make them 16 or 17, or I keep them 13, but I will change the time with 1 or 2 extra questions. Now I'll stop sharing. Okay. Okay, today we will continue about the collisions. We will talk about elastic collision, which is 9 point something, not 8. Elastic. And we will solve an example of that. I think we solved this today, but we will solve also today. Now, in elastic collisions, we have 2 conserved quantities, which are the momentum P initial is equal to P final. Also, we have kinetic energy initially is equal to kinetic energy final. These are the conserved quantities. But in elastic, collision, we have the momentum is conserved, P initially is equal to P final, but the kinetic energy is not conserved. If we have any change in momentum in our system, then we have something called the impulse, which is P final minus P initial, which is vector quantity. Also, if we divide over delta T, this quantity is the force, which is the average force. But if we don't have any change in the momentum, for example, if J equal P final minus P initial equal to 0, how much the force in this case? If this is equal to 0 over delta T, then the force will be equal to 0. You can do this like this and this. I'm doing that. Okay. Now, if we have 2 objects, A and B, and we have the XY plane, I will assume them just move in X direction. B is moved to the negative X direction, and A is moving to the positive X direction by VA, and this is by VB. There is a collision at this point. I'll draw it here. This is B and this is A. Then B maybe, we don't know about the velocities later, but I will assume this, that B will reflect backward and A will reflect to the negative X direction again on XY plane. on the x direction. In this case, if I need to write the momentum before and after, the momentum before is the momentum of all of the system. It's the momentum of PA and PE. Also the same for the kinetic energy. We have kinetic energy for A, which is not a vector, and we have kinetic energy for B. This is elastic. Both of them are conserved. Okay, what we need to write for the first one? The momentum conservation. It's MA multiplied by VA initial. It is in x direction. I will not put a vector. No, I need to put a vector. Plus MB, I will make it now more difficult to you. Multiplied by the velocity of B initially. All of this initially. This should be equal to the mass of A, MA, multiplied by the velocity of A as a vector, plus the mass of B, multiplied by its velocity, but all of this is final. Assume that A and B, MA and B are given, okay? And I gave you the velocity of A and the velocity of B before the collision, and I need you to find the velocities after. So we have two unknowns. Okay, we have two equations. I will use the second one. So we have 1 over 2 MA VA squared. There's no vector here. Plus 1 over 2 MB VB squared. This is initially should be equal to, again, 1/2 MA VA squared plus 1/2 MB VB squared. Finally, now we have two equations, two variables or two unknowns, which are the velocities after the collision. We know how to solve them from math, so it's simple. But if you focus on this, VA here as a vector, it is V in X and in Y. So we have two equations here. So we will have 6 equations. And I need you to find the velocities for A and B in X and Y. It's more difficult. Because of that, I don't need you to deal with this problem in 2 dimensions. I don't need the vector, and we need just to deal with 1 dimension. This will simplify the problem, but and this will keep also the physics. We can understand the concept of collision. Okay, what else? We have, as we see, 2 unknowns, which are the velocity of A and B after. But if you look here, we have a square value. This will give us positive and negative values, and the equations will be more difficult. Because of that, we can assume the next point. We can assume the origin of our X and Y plane, this one, is center at B ball. And we have just the ball A is moving, and we can assume the velocity of B initially is equal to 0. In this case, we convert our frame of reference or XY plane of our system from this, which is the the origin is out of the two poles or the two objects, we move it to this system. We assume that B is a constant without a velocity, has a zero velocity, and B is the same position at the origin. In this case, all of our problem will be more simpler because VB initially will be 0, and this term will be 0. Also, this term will be 0. So our equations now, after remove the vector property, and we assume now the velocity of B is equal to 0, and in any future example or question in the exam, we need to assume this thing, that it's better though. Okay, now we have this equation. Now the total momentum of our problem is just the momentum of the ball A. We don't have any momentum from B. So the momentum initially, which comes from A, is equal to the momentum later, which is for the both balls. It is more simple now, and we can, I think, we have an example after that. Before doing the example, I'm sorry about this one. Okay, now the most important quantities to be found is VA after and VB after, which is finally. We don't need to derive them, okay? And you can use them from the formula sheet. I'll give you, they are given here without derivation. I can derive them, but it's just a math. MA, it is in X direction, as you see here. It is MA minus MB over the total mass, MA plus MB, multiplied by, this is mass over a mass. There is no unit because the kilogram will cancel with the kilogram. We need another velocity because we need the right hand side to be a velocity as the left hand side. Now, the given velocity initially, it is VA initially. And VB, it will be 2 MA over MA plus MB over V multiplied by VA initially. By these two equations, we can find the velocity of A and B after the collision, after the interaction, by using the known things, which are the masses and the velocity of the moving object, which is A from the beginning. Any question about this? Now directly, you can, if you given any example, you can just apply these equations. The next page is numbered by 3. Yeah. No, on the same page we have that example. Page number 2. We have two collide objects A and B with mass A, MA is equal to 2 kilograms. And the mass B is equal to 3 kilograms. The velocity of A initially, this is A, 3 meters per second to the positive x direction. And the velocity of B is 0. Find the velocities after the collision. It's simple. Just use this. Okay, for this example, VA after final is equal to MA minus MB, it is 2 minus 3 over MA plus MB, it is 2 plus 3, multiplied by the velocity of A, which is the 3 meters per second to the positive x direction. I'll put it here just to remind ourselves. Okay, it will be equal to here. This is minus 1 over 5 multiplied by 3, it is negative 3 over 5 meter per second to the positive x direction. Negative 3 to the positive x direction means 3 over 5 to the negative x direction, like this. Negative r, meters per second. It is the same. And you understand that. If you tell me the answer is 3 over 5 to the left, I accept that. To the negative xy, I accept that. Just tell me the direction by your words. What about the velocity of B? Okay, it is 2 multiplied by the mass of A, which is 2 multiplied by 2 over 5 again, multiplied by the velocity of A, which is 3 I have. In this case, it is positive, as you see. It is 12 over 5. Right? Right. I had meters per second. Just tell me to the positive x direction. It is not a vector. This is just a bit of information to tell me the motion for the ball B after the collision is to the positive direction, x direction. Any question about this? Line. Okay. Let us now find the kinetic energy. I told you the kinetic energy should be conserved. Let us check the kinetic energy before and after. Okay, before. Kinetic energy initially is equal to the kinetic energy for A plus the kinetic energy for B, which is equal to 1 over 2 multiplied by the mass of A. That's the law. It's 2 multiplied by the velocity of A squared, which is how much the velocity of A initially? It is 3. 3 squared, it is 9, plus 1 over 2. Mass of B is 3. Multiplied by the velocity square, which is 0 squared. This term will be 0. Okay. The kinetic energy initially is equal to 9 joules. It is not a vector, there is no vector sign. Okay, what about the kinetic energy? Finally, it is equal to the kinetic energy of A plus the kinetic energy of B after the collision, which is 1 over 2. The mass of A is the same. There is no sticky objects here. The mass of A is 2. The velocity of A is negative 3 over 5 squared. The negative sign will go. So it will be 9 over 25 plus 1 over 2. The mass is 3. And we have the speed now is 12 over 5 squared. It will be 144 over 25. This will be equal to 9 over 25 plus I think 216 over 25. This will be equal to 225 over 25, which is equal to 9 joules. Can you see that? Yes, I think yes. Again, we have 9 joules after the collision. We don't have any lost energy or any gain energy. Nobody put energy to the system. Any question about this? We have now, from this example, the momentum, linear momentum is conserved, also the kinetic energy is conserved. Now we have a special case. We will study now some special cases, or I think we have a special case when the mass of A is equal to the mass of B. This happens, we see that many times, maybe if you play glass boards or something like that. The two equal masses, when the first mass come and hit the other mass start moving, and the first mass still with velocity equal to 0 after the collision. It's just like that. If we have the ball A with another ball B, which is equal in mass, this velocity is equal to 0, as we have an agreement from before, and this has a velocity VA before or initial. After the collision, we have the ball A with velocity VA, this is VB, VA equal to 0, and the ball B start moving by VB after finally. This case will be equal to the velocity of A initially. How can we know that? Okay, let us apply here. If the mass of A is equal to the mass of B, this is 5, this is 5. The answer is 0. 0 multiplied by this is 0. Then the velocity of A after the collision is 0. What about this? The velocity of B. The mass of A is equal to the mass of B. So this MA and equal to it will be 2MA, because we have two masses the same amount. Then we cancel this with this, 2 with 2, MA with MA. Then the velocity of B after the collision is equal to the velocity of B of A before the collision, and to the same direction. Any question about this? Because of that, you can see this toy, which is these balls, all of us know it. When all of them have the same mass, right? When we move one of them and let it hit the others, all of them will stay stationary, but the final one will move, which is the logo of our course. Okay, you know this. This is because the conservation of momentum and because the masses are the same. If you pull two masses they will push two masses. Okay. Now, there is an example on the inelastic collision, but it will be done later before the rocket example. Now I will talk about the center of mass. Any question about collisions, like I have a missing part in the center of mass. It's simple to be written, you can write it. Just little drawings. Okay, now, for any object, I'll start by this. This stick, or this one. If I need to make it stable like this, but if I ask you to do that, you immediately come to do this. To choose a point on that object and put it like this, then you can make it stable. Okay, I am asking you now, what about these points here and here? What about the mass here and here? If I have, this is one continuous object. It is the same for any two separate objects, like the sun and the earth, or the earth and the moon. What is this point? Geometrically, now I am asking. This point for this object, it's center, right? It's center in geometrically, but we have also this definition in physics. We have a center of the mass, a center of the mass. For example, if we have two objects, this one is 1 kilogram, and there is a distance between it, the center of it, and another critical identical object, 1 kilogram. And the distance between them is 1 meter, and this is the center between them. If I ask you about the center of mass of these separated objects, you will tell me the center of mass is in the point in the middle between them, here. It is the same as this example. If I put another mass, 1 kilogram, what do you expect? Does the center of mass change its position? I'm asking now. It's the same as if I used my previous example like this, and I hang this object here. Look, there's no stability here. But if I change my center of mass location, stable. Okay, now look. The center of mass changed from 50 centimeters, the half of the roller, to this point, which is 25 centimeters. You expect that? Do you see that? You understand this point? So the center of mass depends, the position of the center of the mass depends on the mass distribution in my system. But if I remove this, there is no stability. Stability happens at the center of mass. If I assume all the mass at this point and I start solving the problem, it's okay. Why we deal with the center of mass? I told you something before, and you see that, and we'll see. I think you will see, and you in the lab, I don't know, but the free body diagram. If we have, for example, this object as the object in the exam, and we push on it by a force, and I ask you to find the forces, you will not draw this system. This is a wall. You will draw just a point, and you put your forces on that point. This is the force, this is the normal force, this is the weight downward, and this is the friction force, right? Why do you choose this point? Where you need to put this point for this system? You can choose a point for a mass, and you need to put this point at the center of mass of that object. For example, we have this system. This is a galaxy, and this is the universe, very big. If we have any other galaxy away from this one, and we need to compute some calculations, we will not assume that the distance between these two galaxies from here to here, because it is not the center of mass. The center of mass of the galaxy at its center, and the center of mass of this galaxy at its center, and the distance between them is the distance between their center of masses. And the galaxy is very, very big. But when we deal with it as one object, just as the eraser, which here, we need to deal with a point within the universe size. Okay. Also, what about? I will talk in general now, then I will put the equations and the other things. In this example, as you see, the center of mass will move to a point closer to the heavier objects, right? Because when I put it this here, the center of mass moved to this point. If we have the sun, and this is its center, and for example, this is the Earth, and this is its center. To know that the Earth doesn't rotate around the sun. It is rotate around the center of mass between the Earth and the sun. The center of mass between Earth and sun, it's very close to the sun's center of mass, because the sun is very huge. For example, if I ask you what is the center of mass, the common center of mass between me and this cup, it will not be in the point between us. It will be in the point closer to my center of mass, which is inside my body. And the center of mass for the Earth and the sun, it is at a point closer to the sun center, inside the sun body. And if I need to choose another two objects, for example, the Earth and the moon. This is the Earth, this is its center, and this is the moon. The moon is not too much small with respect to the Earth, and you can assume, for example, the center of rotation is here, a little bit away from the Earth center. But if the moon is more bigger, for example, like two stars, dual stars, like this, the center of mass will be in a point between them, closer to the heaviest one. I'll put this one a little bit smaller. And the rotation of the objects will be around the center of mass. For example, this will rotate like this, and this one will rotate like this. around the center of mass. So we have two rotations. They will rotate like this around the center of mass. So the center of mass is very important in all physics study. Okay, how to find the center of mass of two objects in one dimension? We'll start with it in just in one dimension. Simply, the center of mass in x direction will be x capital letter like this. Center of mass is equal to each mass m1 plus m2 plus m3 plus blah blah blah, okay, over each mass multiplied by its position, x1, x2, x3, dot dot dot, okay, and this is divided. This is position in meters, but this is not position. This is mass multiplied by a distance. We need to divide over a mass to keep it. Distance is equal to distance. We need to divide over m1 plus m2 plus m3 plus dot dot dot, okay. This is the total mass of the system. And for the y, center of mass, this will be equal to m1 y1 plus m2 y2 plus m3 y3 and so on over the total mass again, m1 plus m2 plus m3, okay, and we have a name for the total mass, which is m capital is equal to m1 plus m2 plus m3 and so on, which is the total mass of the system. So this is the total mass. We can just assume it as a capital M. Any question about this? There is a way to derive this. We don't need to use this way. It is simply to solve it and use it. And the same for the z direction. We don't need to deal with the z direction. Okay, we have example. Let me start by this example, okay, which is just on x direction. We don't have any y direction, but we will solve it for the two directions. For this one, we have 2 kilograms. If we have 1 kilogram and 1 kilogram like this, assume we don't have this one. X, center of mass, is equal to m1 by x1. Okay, we need to suppose or to assume where is our origin. You are free to do that. If you need to assume the origin at this point, it's okay. If you need to assume it here, it's okay. If you need to assume it here, it's okay. If you need to assume it here, it's okay. It's your choice. I'll choose it here. This is the 0. The distance is 1 meter, so this is x1 is equal to negative 0.5 meters. x2 is equal to the positive 0.5 meters. Okay. The mass is 1 kilogram. Okay, 1 by its position, which is 0.5. This one with negative sign. Plus m2, 1 multiplied by 1/2 with positive side over the total mass, which is 1 over 1, m1 plus m2, 1 plus 1 is 2. So this minus this or plus this will be 0. My x center of mass is at x equal to 0 meters. What about y center of mass? Okay, this is simple. The mass one, the y position of this mass, how much is it? The y. The y is 0. Plus 1 multiplied also by 0 over 2, 2 will be 0 also. So the center of mass at 0, 0. This is a dummy example. I have another example here. Yes. I have two masses, A here and B here. Three masses, not one. And C is here. A at the point, it's 5 kilograms at 5 and 2. X5, Y2. Here, B is 10 kilograms at the point 0 and X negative 6 in Y. Mass of C is 15 kilogram. It is at the position negative 3 with negative 3. If I ask you, or we ask anybody, not a physicist, doesn't study physics, where is the center of mass of this distribution? Simply, he will say this part here, this side from this side will be light, this side is heavy. So the center of mass will be in this direction, right? Okay, let us compute it by using these equations, these relations. It will be very simple. These are separated objects. Okay, X, center of mass. Just one equation for each one of them. The first mass, which is A, is 5. What is its X position? It is 5 also. Plus the second mass, B, its mass 10. And its X position is 0. Plus, as we see, the XY plane and our origin is given in the example. What about the mass C? It is 15 kilograms. And its X position is negative 3. Over the total mass, we need to add 5 plus 10 plus 15. 5 plus 10 plus 15. This will give us 25 plus 0 minus 45 over how much? 30. This will give us the position in X is minus 2 minus 20 over 30. This is 30. Minus 2 over 3 meters. Not for second, not for anything. It is just a position. What about Y center of mass? Okay. Again, I will move everything. 5 plus 10 plus 15 over 5 plus 10 plus 15, which is 30. I use everything, but I need to use now the Y direction for the Y position for each one of them. For X, for A, it is 2. For B, it is negative 6. For this C, which is negative 3. This will be equal to 10, negative 60, negative 45 over 30. This will give us negative 3.16 meters. This will be negative 0.67 meter, okay? Both of them in the negative XY plane. This is negative. If this is one, this is negative 3. This I need to put this in negative at negative 6. I'll draw it to be better. So this is at 5 and 2. 1, 2, 3, 4, 5. 1, 2. This is A. B at C. 1, 2, 3. 1, 1, 2, 3, 4, 5. This is B here. This is C at negative 3 and negative 3. The center of mass at negative 0.67 in X direction, it is here. This is X center of mass. It is less than 1. And the negative, the Y position, it is negative 3.16. It is almost here. This is Y center of mass. So the center of mass will be at this point. So it is in the heavy side. Right? Any question about this? Because I will move to the velocity and the acceleration of the center of mass. It is simple. It will not be very difficult because you know that from before. Simply now, you have the position vector. I'll keep these equations. You have the position vector for the center of mass. R for the center of mass as a vector is equal to the negative 0.67 I had, negative also, we have a negative sign. I will clean this, please. Negative 0.67 I had, negative 3.16 J hat, right? Do you remember from before? We have a position vector and we have a velocity vector and we have acceleration vector. We have also these things for the center of mass. It is simple. It will be Vx for the center of mass in I direction plus Vx and Vy in J direction, and also the same for the acceleration. Just to tell you, we have these things for the center of mass. If you need to find the velocity, it's simple. If I give you a velocity for A, a velocity for B, a velocity for C, you need just to change from X to V. Also in Y direction, the same. We have velocity, center of mass, is equal to the first velocity plus the second velocity multiplied by the mass, and so on. Also the same for the acceleration. A1 and A2 and A3 and so on. So we can find the velocity of the center of mass, the acceleration of the center of mass, and so on. What's the benefit of this? I will tell you. If we have a comet, and this comet, as in movies, will hit the Earth, and this is the Earth, and this is our comet. The trajectory of the comet is this. The trajectory of, not the comet, the center of mass of the comet. Sometimes the comet is not just a ball. There are very difficult shapes of the comet. and it's rotating in a strange way. Now, this is the trajectory, and it will hit here. Something in some place, I don't know where, okay? If we send any weapon and explode the comet to separate into different pieces, these pieces will stay distributed about the original center of mass. The motion of the center of mass will continue the same. And these pieces will distribute around the motion of the center of mass, like this. And these pieces will hit the ground in different places. And these places, if you need to compute the position of the center of mass, it will stay the same. So the motion of any system is ruled by the motion of the center of mass. For example, the sun and the planets are moving together following the center of mass of the system, which is the sun almost. Planets, all the planets will not affect the center of the mass of the system because the sun will dominate everything. Is this point is understood? I will show you the experiment. I will carry many objects, chalks, and I think this is enough. I think if I throw them like this, the motion of them, all of them, just like a motion of one object with one center of mass, which is their center of mass. Okay? Is this point understood? Any question about this point? Also, if we compute the acceleration, we have very important idea. To be honest, I will not ask you about it, but I need you to know this thing. We can compute the force on these things. For example, if we have the velocity of a center of mass is equal to m1 v1, assume it's in x direction, okay, plus m2 v2, and so on, divided over 1 plus m2 plus everything. We say from before, this is the total mass of the system. If we multiply it, because this 1 over 1, if we multiply it by the velocity, this will be the velocity of the center of mass multiplied by the total mass is equal to m1 v1 plus m2 v2, and so on. m1 v1, it is the momentum for the first object. This is the momentum of the second object. So the momentum of the objects, the parts of the comets, all together, the momentum will be equal to the momentum of the comet, which is the center of mass, or the total momentum. Also the same thing, we have the acceleration of the center of mass. If we multiply it by the total mass, will be equal to m1 a1 plus m2 a2, and so on. This is the force on the first part, the force of the second part on the second part, and so on. It is equal to the total force. So the center of mass is very important to be studied. Okay, this is the part what is covered in the notes, and I need to now to tell you before solving the example in the collagen. Now we have page number 7. I finish it, and you need to write maybe or draw something. It is very simple, and you know it before I tell you about it. Now, what if we have an extended object like this one, and this length is 1 meter? If I ask you, where is the center of mass of this this geometrical shape, if its length is L, where is its center of mass? You will tell me it is the geometrical center, which is L over 2. What if I give you this square, L? You will tell me it will be in the center, and you are right. If I give you also a rectangle, you need to divide it like this, it will be in this center, or like this, it will be in the center. If I give you a circular, you will tell me it is at the center, and so on. Any uniform geometrical shape, it is easy and simple to find its center of mass. Do you know what? I'll give you a question like this one. But I will make it simple. This is a hint for the exam. What if I give you this shape? You have this shape, and you have a triangle also here. Equal lengths here. For the triangle, if we have this shape, which is a house, for example, and I ask you to find the center of mass of this shape, you will tell me it's okay. I will divide it to different shapes. This is a square, and this is the center of mass. This is a rectangle, and this is the center of mass. This is triangle. I can divide it, take a half of the angle of each head, and I will put the half of each side. This is the center of mass. So we have this is center of mass, this center of mass, this center of mass. If you know X and Y for each one of them, then you can tell me where is the center of mass of all of them. What if I give you this shape? Where is the center of mass of this shape? Who can tell me? It is not a uniform geometrical shape, right? There is a way. When I was in your place, my first, I don't know, maybe 2 or 3 weeks like this, I answer this question. I feel myself as a hero. It's by hanging. By hanging means, I will do this experiment now. If we have a uniform geometrical shape, it's easy to find its center of mass. But if we have a non-uniform, we need to hang it at a point. Then it will be like this, for example. We can draw a line downward. Then we need to hang it from another point. Then draw a line downward. The intersection between the two lines is the center of mass. For example, this is a rectangle. It is simple to find its center of mass. I will draw lines like this and find the center of mass, and it's easy to know it's at this geometrical shape, geometrical center. I think you can see me. Yes, you can see. I'm not cheating now. I'm doing that. Okay. This is the center of mass. It is the geometrical center. If I try to hang it, I will make a hole any point I need. From that hole, I need to draw a line downward from the back. Or from here. I'll use a different color. You will not recognize the colors, I know that. My line will be like this. If I hang it from a different point, from here, for example. And I hang it again. The hanging way, the shape of the hand object will be rotated about the center of mass. It will be still the same. What if I change the shape of this? Do you expect the center of mass will still at the same point? I'll just cut it from here, for example. I remove part of its mass. Like this. And I will also remove another part from here. Because of that, you can find this is different shape than before. This is the center of mass. In the school, when we teach this, we give the students the map of their country. And we need to find the center of mass or the center of that shape. Now I have 2 points. If you need to choose any, look for the 2-dimensional objects like this, which is just a plane, 2 points are enough to find the center of mass. But if you have an object like a potato, you need 3 points. 3 points will define the center of mass at inside the potato. Okay, where's the pen? This is the pen. I'll now do this again using the blue color again. I'll use with the move color. Okay. I don't need it to be the same. Like this. What about this one? It's the same almost. If I change it like this. I'm free to do that. This is another center of mass. The same. I need to make it away from the original one. Okay, can you understand this point? So if you have any non-uniform shape, you can find its center of mass by doing this. The center of mass is changing from point to point after changing the shape. Okay, it's moved from the center to a different point on that surface. Okay, any question about this? Now, okay. I will deal with 2 examples. One of them is the inelastic collision, but in 2 dimensions. If we have this problem, which is, for example, maybe it's a car hit by another car. The first object comes from negative y direction. The second object comes from the negative y. This is from the negative x, I'm sorry. So this is A. This is A with M mass equal to 900 kilograms. and velocity is equal to 15. Assume it as a 15 in J hat meters per second. Okay, this is B, has a mass equal to 1800 kilograms and velocity initially is equal to 7 meters per second. Do you understand the initial conditions? They are sticky. Maybe they are cars, and after the collision, they still as one mass, and they will move to this direction, like this. They became one object. Find the velocity after. The mass is, we can find the mass, it's simple. We need also to find the angle. Okay, we have the moment, the momentum will be conserved before and after the collision in both directions, x and y. The kinetic energy is not conserved. We don't need anything to do with the kinetic energy. Okay, the momentum in x direction, we have momentum initially in x is equal to the momentum finally in x. The momentum initially in x, it is ma, it is the momentum of the first object plus the momentum of the second object. The momentum initially, P initially as a vector, I will note here. P initially as a vector is equal to that momentum in x direction, which is mb, or the first object, or ma plus pb, the momentum of A plus the momentum of B, which is equal to the mass of A multiplied by the velocity of A as a vector, plus the mass of B multiplied by the velocity of B as a vector. So this is equal to ma, the velocity of A, it is 7 of A here. The mass of A is 900. Multiplied by the velocity. The velocity, it is 0 in I hat plus 15 J hat. This is initial. Plus the momentum of the B object. It's the mass multiplied by the velocity. The mass is 1800 multiplied by the velocity. It is 7 I hat plus 0 J hat, right? This velocity to the positive x direction. So the momentum is equal to 900 multiplied by 15 in J hat plus 1800 multiplied by 7 in I hat. So this will be equal P initially. $13,500 I hat plus 12,600 J hat. This is the momentum initially. It's a solved here, but I'm solving it step by step. What about the momentum finally? It is the momentum of just one object. Just we have one object. This should be equal to the momentum finally, which is equal to the momentum finally is equal to the mass, the total mass, which is MA plus MB, multiplied by the final velocity as a vector. Okay, this is equal to MA plus MB, it is 900 plus that one, which is 2,700 kilograms, multiplied by the velocity final in x and y, because it is a vector. Okay, now we have one equation, one unknown variable. Now we have can remove this now, we don't need it. Now we have P initially is equal to 13,500 I hat plus 12,600 U J hat is equal to 2,700 V of all the objects, or both objects, which is V finally X I hat plus V finally Y J hat, right? It's a vector quantity, this velocity. And you see that our object became to this direction with V finally and with theta. It is simple to find that now. Just divide over 2 7 zeros, 2 7 2 7 zeros. Okay. Now you have this thing. Where is the one here? After dividing, you have this over this will be equal to 4.67 meter per second I hat plus 5 meter per second J hat. This is equal to V final. This is V final in X direction, this is V final in Y direction. Just I divide this over this and this over this, this is 1. I find the velocity. If I ask you about the speed, simply use this relation. We don't know, we know this relation, which is the Pythagorean theorem. Vx squared plus Vy squared. This is the speed, not the velocity. This is the velocity, this is the speed. What is the theta? Yes, Salam. It is tan inverse to Vy over Vx. I think I found it here. I didn't find the speed in that page, the second page, but theta is equal to 46.97, almost 47 degrees. Okay. This is all about this example. You just need to deal with X and Y separately. If you need to deal with them all together, simple. I have a question like this. In tomorrow's exam. Okay, any question before I talk about the rocket problem? I will discuss it and I have a question. We learned from before that we have a Newton's third law, which is for any actions there is a reaction, the same force magnitude in an opposite direction. Okay, that if we walk on the ground, then the action on the ground, the reaction on our body. Some students asked from before, what about the rocket? The rocket is outside in the space. There is no ground to hit it and then to have a reaction. When the rocket at the ground, it's okay, they told us. They asked, they try to make themselves as they are not physicists at the end. They ask the rocket at the ground, we have a force, action, and we have a reaction. Then the rocket will start moving. And later, there is the air particles, and the rocket is here, and it hits the air particles, and it is moving. We agree with that. They told us this. But what about if the rocket outside the Earth surface and the Earth atmosphere is here? Or if it is a space shuttle, you know it. What's the name of it? It is moving. There is nothing to do with the action and reaction forces. There is no ground, no air particles. This is not the point. We have, I told you from before, we have equations of motion, V2 equal V1 plus AT and so on. Then we have the upper level, which is Newton's laws. Then we have the energy and work level plus the momentum. When he asked us about this, he just used Newton's law. He don't know enough about energy and momentum technique. We have this technique, and we can answer this question by using this technique. The rocket or the space shuttle outside, without existence of any other object to interact with, because the conservation of momentum, these vehicles are still moving. For example, if you are here, or me, on this wheel, I cannot drive this wheel, and I have a ball, and I throw the ball to this side. Okay. Yes, the ball will go to this direction, and me will go to the opposite direction, just like the bullet and the rifle. If there is also the boat, and this is a shore, there's a person here, need to jump from here to here. He will fall in the water because the boat will go backward, and his action just will keep the center of mass of him and the boat at the same place, and he will fall here. He will not reach this point, for example. Because just not action and reaction, because the conservation of momentum. Now, what about the rocket? Okay. We have the rocket. We also know that any change in momentum during a time will give us a force. And this force is equal to the mass multiplied by the acceleration of that mass. Assume the mass of our rocket is very big and it's almost m. I will give it mass capital M. And you remember that from before also, m A as an average acceleration is delta V over delta T. Yesterday, I told you, if the mass is constant, I need to put it here. So it will be delta MV. Delta MV over delta T. So the delta will affect on the mass and on the velocity in the momentum. In this case, the momentum, now we have this thing, delta T. The mass multiplied by the velocity, this is the momentum. This is this term. The change will apply twice now. We have a change in velocity. Yes, we have, it's an acceleration. Do we have any change in the mass? If we look to ourselves at our examples before, we don't have any change in the mass. But now, we have a change in the mass. The rocket throws some material from it, which is the fire fuel, outside of it. So we have a change in mass. So in this case, we will put the change in momentum like this. It is the mass multiplied by the change in velocity with respect to time, plus the velocity multiplied by the change in mass with respect to time. We consider the two changes, the velocity, which is the acceleration, and the change in mass, which is the lost mass. So we have a change in momentum with respect to time. This will give us the force. All of this is equal to the force, which is Newton's second law. I don't need that vector from now. Look, forget this term, the second one. You have m delta v over delta t, which is the acceleration. This is Newton's law, equal to F. This is the known Newton law, this term with F. This is the first or the ordinary formula of Newton's law. But the strong formula or the full formula of Newton's law is this one, with the change of mass. Now, let us solve an example. We have change in momentum of equal to the force. This force will act on the rocket and make it move forward. Okay, we have, in our example, we have this rocket. This rocket ejects 750 kilograms. So 750 kilograms every second, every minute, or every 60 seconds. Okay? This is the change in mass. Okay? This is delta M over delta T. This one. The velocity of the exhaust material is 85. The velocity of these things is 85 meters per second. So now I give you the change in material and the velocity. Okay. With assume that the motion to the positive x direction, this is the acceleration. and the velocity of that rocket, and the velocity of these things to the negative x-axis. So we have a negative sign here, or negative I. What is the force effect on this rocket? Okay, now the force, this is the force, is equal to this. These ejected materials will work as a person, and this person is pushing the rocket forward. We need to find this force. It's okay. The force by the exhausted material is equal to the velocity, this term, V delta M over delta T, which is 85 multiplied by 750 over 60 seconds, because the time is a minute. This will be equal to how much the force? It's negative 1,062.5 newtons, right? The force of these things backward is this. What is the reaction? The reaction on the rocket, the force on the rocket is the same as this with negative sign, which is 1,622.5 newtons to the positive x direction. This is to the negative x direction. If I give you the mass of the rocket, if the mass of the rocket mr equal to 20,000 kilograms, 20 tons. What is the acceleration? Just divide the force on the mass, F, over the mass is equal to acceleration, which is equal to this 0.053 meter per square second. Accelerated slowly. If we need to increase its velocity more and more, we need to fire more material outside from this rocket. Any question about this? This is the main equation for the rocket problem. We don't have any change in the velocity of these materials. These materials' velocity is constant, which is 85 meters per second to the negative direction. So any change in this velocity is zero, because the velocity 85 minus 85 over delta T equal to 0. So this term is 0. This is all for this material. I'll start putting the review for the exam from now on, and good luck in the exam tomorrow. And again, please, if you need anything, just contact me, send an email, or just, you have my phone number. You can send a message, because sometimes I'm away from the PC. I was recording at this point. Thank you.